Okay, here is a heating cooling problem from a exam a few years ago. It's a diploma problem, and we're melting down diplomas to make a big diploma. So it's a Newton's law of heating and cooling problem that tells you that in the problem, and the that relates temperature between an object and an environment. Here, the object is a bunch of diplomas, and the environment is a 2000 degree foundry. So let's model that equation. If big T of little t is object temp and its diplomas, then T of, say, an environment or a medium is the temp of the foundry. And our equation all the time for Newton's law of heating and cooling is T prime, or d big T over d little t, is constant K times temperature of your object minus the temperature of your environment. And in this case, that's d big T over d little t equals K T minus 2000 degrees. And we also have the initial temp of the diplomas, and it was 70 degrees room temperature. Then if we're going to, so there's our initial value problem that we need to write. Initial value problem, here it is. There's your differential equation and your initial condition over here. Then to solve this, if we're going to find an explicit solution, you could, let's see, what are your options? You could use separation. You could use integrating factor. Could you use muck? I believe you could, because you have constant coefficients on the dependent terms. But this is also one just to know. So if you did want to see how to solve this, maybe I'll make a separate video or look back in other videos. But the solution for this is one you should know, and it's AE to the K times T plus the initial environment temperature. And then we could use our initial condition to figure out A, and then we could use T of 5 being 1000 to figure out K to get an explicit solution. So let's do that. If we use, let's recover A with T of 0 is 70. So 70 is AE to the K times 0 plus 2000. So 2000, if we divide or subtract, I guess, then we would end up with, what would that be? That would be negative 1930 is A e to the 0, so e to the 0 is 1, so A is negative 1930. Let's update our model or our equation with big T of little t is now negative 1930 e to the kt plus 2000, and we could find K. So let's recover K. With T of 5 is 2000. Again, I made that condition there. And so if we plug in 2000 equals negative 1930 e to the K times 5 plus 2000, we would have, let's see, we need to move 2000 over to the left. That would give us 0 on the left, and then divide by negative 1930. That doesn't seem like, oh, did I? Okay, I wrote that wrong. T of 5 would be 1000. It would be bad if we ended up with 0 on the left. Okay, so now if we move the 2000 over, we get negative 1000 divided by negative 1930 is e to the K times 5. We need to solve for K. So let's take the natural log of both sides. What just happened? There we go. If we take the natural log of both sides, we have natural log of 1000 divided by 1930 1930. I know we could reduce that, but I'm not going to. Natural log of the left, e to the k times 5. So this is natural log 1,000 over 1930 is equal to k times 5. And then let's divide by k. So this would tell us that, so k is equal to natural log 1,000 divided by 1930 divided by 5, so a fifth. Then I'm going to make that a little smaller. And then, so let's resize. There we go. Okay, so then our explicit solution is big T of little t is A, which was negative 1930, e to the k times t plus 2,000, and k is a fifth natural log of 1,000 divided by 1930. Great. And there's our explicit solution. Now that you have A right here, now that you have K, then this is good for, inputting time and outputting temperature of the diploma. So for example, if we were asked, let's find at what time the diplomas are at particular degrees, like 1,500 degrees, then we could set the left side equal to 1,500 and solve for t with some algebra. But here's your equation, and there you go. Hope that's helpful.